The equilibrium constant. A reactant's equilibrium constant allows us to determine the quantity or concentration of the reactants and products in a system once the system reaches equilibrium. To find its value, we use the following formula, where K represents the equilibrium constant, and where the activities of the products are in the numerator and those of the reactants are in the denominator. The coefficient of each reactant and product in the balanced chemical equation becomes an exponent on the corresponding activity value. In the formula, only the gaseous and aqueous compounds are considered. The activities for gases are measured in atmospheres, and the activities of solutes are measured in moles per liter. Solids and liquids take an activity of 1, meaning that any reactants or products in solid or liquid form do not have an effect on the calculation. We solve equilibrium questions using ICE tables, where ICE stands for initial, change, and equilibrium. There are lots of factors that need to be considered to find the answer to this question. Let's start by writing the formula for the equilibrium constant. Note that we always place the products in the numerator and the reactants in the denominator. We also need to remember that solids and liquids are not used in this calculation, so we ignore compound E and exclude it from our ICE table. Placing the rest of the reactants and products into the equation, we also have to remember to put the coefficients as exponents on the corresponding values. Next, we can place the values of the concentrations given to us in the question into our ICE table. Unless it says otherwise, we never start with any products, so we put zeros in the initial row for both products. The concentration of C at equilibrium was given, so we put that value in the equilibrium row of our table. Now we determine how much each compound's concentration will change. We use x as our change variable, as well as the coefficients from our balanced equation, which will make the change unique to each compound. We get minus x for A, minus 2x for B, plus 3x for C, and plus x for D. Note that the reactants always have minus x and the products always have plus x. Since we have all the values in our table for C, we can use this information to solve for x, which gives us 0.15. We can then use this to find the equilibrium concentration of the rest of the compounds. Finally, we place the equilibrium concentrations of each compound into our equilibrium constant equation. Remembering not to forget to include the exponents on each compound, we get a value for our equilibrium constant of 3.9. The value of K allows us to determine which side of the reaction will be favored, reactants or products. If K is greater than 1, the equilibrium will favor the products and be pushed to the right. If K is less than 1, the reactants will be favored, and the equilibrium will be pushed to the left. Since we got 3.9, which is bigger than 1, we know that our equilibrium will favor the products. The value of K can also be determined using the partial pressures of gases. We use the same formula as before, we just simply use partial pressures instead of concentration as our measure of activity. Looking at this problem, we start by analyzing the data that was given to us. On the reactant side, A is a solid, so we know it will not appear in our equation. We just replace it with a number 1. Note that the question also says that we only have A initially, so we can put zeros in the initial row for both products. We also know that the total pressure of the gases, B and C, is 8 atmospheres. The total pressure can be represented with the formula PB plus PC is equal to 8. Now let's look at the change row in our ICE table. Again, we use the variable x along with the coefficients of our compounds. We get plus x for B and plus 3x for C. From our formula for the total pressure, we can set x plus 3x equal to 8 atmospheres. Solving for x, we find that x is equal to 2. Then we can use this information to fill in the equilibrium row of our table. Don't forget to multiply x by whatever coefficient each compound has. Our equilibrium value is 2 atmospheres for B and 6 atmospheres for C. Finally, we can put these values into our equilibrium constant equation. Remembering that equilibrium constants do not have any units, we get a final answer of 432.